Today we will be talking about lines in 3D. So I'm starting off the video in Desmos because it's actually way easier to know what you are doing the math for if you know what it looks like. So first thing I'm going to do is show you that a line drawn in 3D, a line that looks like this, will be calculated by a vector. Just the tip of the vector constantly dragged along in 3D space. And if you plot all the points, the infinite many one-dimensional points along this two-dimensional line, you will get a line. And I'm sliding the value that I set for t, technically, which I'll show you inside when I show you the math. But basically, this line is the plotted points. So let's say this red circle here, that's one of the points. Another point on that red circle, another point on that red circle. These are the plotted points of this resulting vector, which draws this blue line. And we're going to learn how to calculate, or how to show you how to represent this purple vector in your notebooks or inside of your papers, tests, or whatever. So I'm going to show you, hold up, let me actually write down, let's write lines, make it look actually decent handwriting, lines in 3D. Yeah, it looks terrible, hold up. Lines in 3D. So I'm going to show you the first form, which the first thing that I learned on it. But basically, what a line in 3D is, it starts off with, I don't know, a vector, some vector that has an x value, a y value, and a z value on that line. So this point right here has to be a value on the line. You could choose anything, honestly. And the next thing is plus t and any vector that is parallel to that line. So what I mean by parallel is basically it's going in the same direction. Anything that's, you could put the vector anywhere on your 3D Desmos and it would be parallel to that line. So let's say P1, P2, and P3. So how this formula works is any point on that line, let's draw a little picture here. Any point on this line here, let's say that point is here, right? So that point, let's say this point is the red thing, and let's remove this underline because I don't like it. It's this red dot here. And then let's say that this vector is parallel to, and let's say the vector points like here, parallel to the line that we're supposedly drawing. Whenever you increase t, this vector will, well, increase, because when you multiply a scalar by a vector, the resulting scalar the resulting value, or the resulting vector, will be parallel still. So t times p1, p2, and p3 is still parallel to the previous, just base p1, p2, and p3. So they're all still parallel. whenever you multiply t by this guy right here, the vectors are also parallel. What does that mean? Why is that important? Well, if you multiply t by, let's say, 1, so basically just this vector by itself, you just get the same vector down here and up. Now, what if you multiply it by, what if you set t to 2? Well, this vector would be double the length. It would be up here. What if you multiply t by -1? Well, the vector would go the opposite direction from this point because we're adding it onto this point. And here's the thing, I'm representing this in vector form because this technically is just this right here. So this vector points to somewhere. And then as we multiply t by any value, this green vector will always be parallel. What does that result in? So let's say we set t to -1. Let's try to make this approximately the same length as this. Look, as we keep multiplying t by any value, these vectors just get longer and longer, or these vectors just get longer and longer the opposite direction, starting from this point. And I'm going to show you that it doesn't matter what point you set, right? As long as you choose a point on the line. Let's say we set the point to here. It still will give you a line, given this formula. So you can actually represent this in a different way. You can represent it in something called I think it was like vector valued function. I don't know. That's probably something different, but don't quote me on that. I'll just show you the other form. You don't even need to know the name. Just know how to do the math, and you'll get a good grade on your exam. So I can actually represent this vector as x1 plus p1t, comma, y1 plus p2t, comma, z1 plus p3t. So, as you can see, all I did was just plug in x1 into this, plug in y1, and plug in z1. I just plugged in p1 to the x because p is the corresponding I hat value or x value. P2 is the corresponding j hat value or y value. So I plugged in p2 into the y value part of this. And then I plugged in p3 into this. So these are the two ways you could represent a line in three-dimensional space using vectors. But the reason why I put the t here is because imagine you just distributing this t along every single one of these. And honestly, I'll actually show you how I figured this out. Or not how I figured this out, well, how I distributed it. But honestly, you can just x1, hold up, I'm going to write down the previous form, x1, z1, plus, if you distribute the t into every single p value here, you just get p1 of t, p2 of t, and p3 of t. And if you add all the corresponding components of each vector here, you get the same thing as what's up here. So these are the two ways you can represent a line in 3D. Now let's move on to some practice problems. These are going to be some, I guess, smaller practice problems. They're not going to be as difficult as what you would see probably in class, but I'll just say that there's going to be point P, and point P rests on the line that you are supposed to draw. We say we have point P, and the vector that is parallel to this line is 3, 4, 6 or something. Represent, or at least try to represent this right here. Use this, given this information, try to represent it in a line using any of these forms. Okay, so how we're going to start this? Well, we're going to start it by plugging in whatever's in the points into this part here. Because remember, this part of the formula is any given point on the line. Doesn't matter, just choose one. So x1 is 1, y1 is 2, and z1 is 4 plus t. And remember, this vector is parallel to the line. So whatever is here, this vector, any vector that is parallel to the line works. So we could also use, like, I don't know, this is also parallel, 6, 8, and 12, because we multiplied each of the values inside of this previous vector by 2. So any parallel line works. We can honestly plug this one in, and I'll just do that, actually. You know what? Let's just use the information that you guys got. 3, 4, and 6. That's all. It's honestly, when you're given information, it's honestly just plugging it in and then doing something with it. And I'm going to represent it in this form. So we'll just add everything together. This doesn't even require memory, honestly. As long as you know this, you can get this pretty easily. 1 plus t times 3, comma, 2 plus 4t, and negative 4 plus 6t. And the reason why I chose negative 4 here was because negative 4 is here. If this was negative 6, then t would be, this right here would be negative 6. Okay, let's go into another one. Let's continue on. I'm going to say that there's a point P with values negative 3, I don't know, 2, negative 8. And I'm going to, instead of drawing you or telling you what the parallel vector to the line, I'm going to make another point. So on the line. So P and Q are both on the line. 1, 3, negative 12. So these are 2 points that are both on the line. Solve for the equation of the line. Okay, so the first thing I'm going to do is find the vector between points P and Q. And the reason why is because points P and Q are both on the line. So if you sort of imagine these 2 points connected together, or from P to Q, that vector is actually parallel to the line that we are trying to represent. So from negative 3 to 1, what value do you have to add negative 3 by to get 1? You go up by 4. From 2 to 3, it's 1. And from negative 8 to negative 12, you actually have to go down 4 values. Now, the order in which you represent this vector matters. If you did Q to P instead, it would be different. Everything would actually just be the opposite values. And the reason why is because if you go from the value of Q to P, 1 to negative 3, you have to subtract negative 4 from 1 to get negative 3. You also have to decrease 3 by 1 to get 2. And from negative 12 to negative 8, it's actually an increase into 4. But we'll use PQ as the parallel vector. It doesn't matter which order you actually write it in because both the vectors are still parallel. They're just going in different directions. So we have a point. Pick either P or Q. Doesn't matter. We have just a point on the line. Let's write it down. Let's just basically copy this format up here. Negative 3, 2, and negative 8 plus t of any vector that is parallel. We determined that P to Q is parallel, so we're going to write down that vector. And now we have the format for the line that we drew. You can also use this form whenever you're going to be doing math. You are likely going to use this form. This one up here is just to represent the line. Probably what you would type in Desmos, to be honest with you. Or actually, you could type in both in Desmos. That's what I did on the representation or visualization earlier in this video. But let's write these as, let's write this form, sorry. So we start off with -3 because that is the value we put into here. And distribute t into 4. It's +4, so we do plus 4t. Start off with 2 plus t into 1, so it's just 2 plus t. And at -8 minus 4t because it's a -4 here. And these are both the representations for this line that we're supposedly drawing that have these 2 points in them. Let's do one more. So let's say we are given point P again. I don't know, -10, 3, 8. So we're given Q. -8, 6, 2. So go ahead and write the line form for P and Q. So I'm going to start off by writing the vector P and Q. And let's write the vector from P to Q, not Q to P. So what do you have to do to -10 to get -8? Well, you have to increase -10 by 2. So 2 goes here. 3 to 6 is 3. And 8 to 2 is subtraction of 6. So right here, we have 2 points that are both on the line. And all we did was just solve for any singular vector on this supposed line that we're trying to represent. And then we got 2, 3, and -6. Now all we have to do is write down this form up here. So this form calls for any given point. Remember, it's any point, doesn't matter. Just solve for one. -10, so we're going to use P. -10, 3, and 8. Okay, that's supposed to be a vector. Plus T. Any parallel vector goes into here. It's 2, 3, and -6. So 2, 3, -6. There it is. This is this form up here in the line with these 2 points. So whenever a question is giving you 2 points and tells you to draw a line, it either asks for this form or this form. Doesn't matter. Okay. And when you're giving 2 points, you can draw the vector between these 2 points. So P and Q, the vector between P and Q. And that resulting vector, so this vector over here, will give you a vector that is parallel to the line you are supposed to draw. And since this vector is parallel to that line, you can just plug it into the equation up top. Now let's just represent it in this form. -10 plus t plus 2t, 3 plus 3t over here, and 8 minus 6t, 6t from there. Oh, let's draw the end. But this right over here is what you really have to memorize. Once you have this form down, then you'll have this one nearly all the time. And this one you're going to be typically using to solve for math equations. So memorize this. I'll review this again. This point right over here is just any point on the line. Choose any point on the line. And also, this vector here is any vector that is parallel to the line. So what I mean by that is, since this vector is parallel to the line that we drew over here, we can actually just, let's say we got something different. Let's say we multiplied this vector by 2. This is still parallel because since we multiplied a scalar by a vector, the resulting vector will be parallel to this. Even if you did this by 3, even if you multiplied this vector by 1/2, the resulting vector will always be parallel. So if you have any questions, put it down in the comment section.